Hi everyone, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements, and welcome to another Workbench Tips video. And in this video we're going to be discussing how to use symmetry in Ansys Workbench. So we're going to be talking about various different types of symmetry in this video today. First of all, we're going to talk about using symmetry with truss and beam models. Then we're going to move on and talk about using symmetry in 2D and planar symmetry. Then we'll talk about using symmetry with 3D models. And finally, we'll talk about using axisymmetry and cyclic symmetry. So first of all, let's take a look at a truss problem. So this is a typical truss problem where we have a bridge and it's got a fixed support on either end and it's got a force for whatever reason at this point here, and this force is equal. So remember to use symmetry, not just the geometry, but the loading and supports must be symmetric as well. So in this case, we have a symmetric geometry, the symmetric loading, so it's the same on both sides and in the same position on both sides. And we have a support which is the same on both sides in the same position. So if we were to draw a line down here to the middle of this bridge type structure, and we were to just simply mirror one side over, we'd get the full structure. So in this case, our finite element model of this bridge is going to look something like this. We're going to use 4 truss elements. So we have one truss here at the top, one here, and one here. We fix this point here. We put a load on this point here, and we're going to define a symmetry edge on these points here. So in other words, we're going to tell this model that it's reflected about these points here, and it's reflected in this direction, in the horizontal direction, which is very important. So it's important just to point out that a lot of the times defining a symmetry constraint or symmetry edge is the same as actually defining a frictionless support. So if you think about it here, if we define symmetry, we're going to allow this point to move up and down, but we're not going to allow it to move left and right, and similar with this point here. That is effectively the same as putting a frictionless support on those 2 points as well. So these 2 things are equivalent and should give you exactly the same results. In some, if you're not using Ansys Workbench, for example, you may not see the term frictionless supports. It might be called something else, or you may not even have a symmetry available. You may have to use frictionless supports. So let's go over to Workbench and see how we use symmetry with truss models. So I've already built a very simple truss model here. So again, it's half the bridge structure like we just showed in the previous slide. So you can see we have one truss here and then a triangle of trusses here. And I've gone ahead and defined a circular cross section again, which is defined onto those lines, and that gives me a line body which I can then take into my modeling part of Workbench. So if I go and take a look at that, I've brought that in here. So you can see I brought in my geometry import. My geometry is made of a line body, which is as I had in the design modeler there. I've just defined some properties for steel, called it my steel, and used that as the material. The cross section again has come across, circular cross section. And I've already gone ahead and I've just defined some edge sizing. So I've said I want to use 1 truss on each of these lines, and I've gone ahead and meshed that so that we're all up to that point. The next thing I can do then is go ahead and apply a force. So you can see I've applied a force up here at this node here, this point here, and I've applied a fixed support down here. So again, it's exactly the same as the model shown in the schematic a little bit earlier. The next thing I have to do now is apply symmetry here to these points here. So how I do that, you may notice if I go over here to model, I don't have a symmetry option. So what I must do is I go up here and I right click on model and I go insert, and I have here. Okay, so I click on symmetry and it opens up the symmetry folder here. Again, I click here on symmetry, right click. I'm going to say insert symmetric region. Okay, so now it's saying I have a symmetric region, but it's not defined. It's asking me what geometry do I want. Well, what I want to do here is I want to click these 2 points. So I make sure up here in my selection that I'm selecting a vertex. Okay, I'm going to hit the control key and I'm going to keep selecting both of those points. I'm selecting 1 and 2. And then I come back over here and I go apply. So now it's picked those 2 points. And the next thing, which is very important here, is where is the symmetry normal? What direction is the symmetry normal pointing in? So in this case, I want it to be the x-axis. In other words, I want my model reflected over in this direction. So the normal to the reflection plane is the x-axis. So in this case, the reflection plane would be defined by the y and z axis. Okay, so y is going up this way, and z is coming out of the screen. So the normal to that plane is x. Okay, so now I've defined that, I've defined my symmetry region here. So now what I can do is I can go ahead and solve this really quickly. So now I've solved that. I already set up some results that I want, so I can look at the directional deformation, so I can see how much the bridge is deformed. So again, this point hasn't moved, and you'll notice these points have stayed on the symmetry plane. And again, just to check that, I'm going to go up here and show the undeformed model as well as the deformed model. So you can see here that those points have been allowed to move up and down, but they haven't moved across the symmetry plane, which is what I want to happen here. And again, I can go and look at other types of results if I want, but they will all essentially be the same. Okay, and the final thing we're going to look at before we move on from this truss model, then often, you might want to take a look at the full model, even though you've modeled only half of the model. So in the later versions of Workbench, this is possible. So if we go up and click on Symmetry again, you'll notice here we've got this graphical expansion menu coming up here. So what I'm going to do here is you notice the first thing here, we have number of repeats is 0. So I'm going to change that to 2 because I want two versions. I want the original version and the mirrored version. I change the method to half, okay, because I only have half of the thing. And then I need to put a very, very small number in here, so just a little bit of an offset. So what it will actually do is it'll put this small gap in between this model and the reflected model. So again, I'm just going to put in 1 e to the minus 6 here. Okay, and now you should find that if I go back down and look at my results again, now I'm getting the reflected model across. Okay, and again, I should see that in my mesh as well. Okay, so that can be handy when I want to visualize the full model, or if I'm showing results to clients or whatever, and I want to, I've only modeled half of it and I want a quarter of it or whatever it is, and I want to show the full model. So again, just going to go in and turn that back off again. So I go into Symmetry here, and I'm going to get rid of that little gap. I'm going to turn that back to full, and I'm going to get that to 0. They were the original settings. So now when I go back down to my results, I'm just getting half the model again. So next we're going to look at planar symmetry in 2D. So we're going to use the old classic plate with a hole problem here. So I've done a full video on how to actually do the plate with a hole analysis, and the link is given down here, and I'll try and add a link into the video as well and put a link in the description. But just very briefly, if we look at our plate with a hole problem, so we have a plate with a hole that's symmetric about two planes. So if we have a plane through here and a plane through here, it's symmetric in both those directions, and we have the same force applied either side. So we have our geometry that's symmetric and also our loading that's symmetric. So again, if we were just to take this cutting plane first of all and just take this half of the plate and load, it would be symmetric across this way. But we can also take this cutting plane as well and then divide our load in half, because it's applied over just half of the line on the edge here. So we can model 1/4 of the plate, scale our load by half, and that's essentially the same as modeling the full plate with the full load on either side. So again, we have this situation here where we've got 1/4 of the plate, we have a symmetry constraint on this edge, a symmetry constraint on this edge, and half the load applied. Or if you don't have symmetry available in your particular FEA software, you can use a frictionless constraint as well. But in this case, we're talking about Workbench, and we do have symmetry available. So let's just jump into Workbench and see how we go ahead and do that. Okay, so I have my Workbench project open here. I've already defined a geometry. So I've, again, the usual thing, made a sketch, made it into a surface body, have my geometry. Again, this is all covered in the other video, which I'll link if you want to take a look at that. And I've pulled that into my mechanical analysis. And again, you can see here I've got my geometry import here, which is one surface body, which has a material assigned to it. So again, material my steel is assigned. I've gone ahead and done some sizing on the mesh. Just this isn't the best mesh in the world, but for our purposes here, it's okay. So basically, I've just put a sizing on the line here and biased it so that the elements on one end are bigger than they are at the other end. Did the same thing on the bottom line here, and then just put a number of divisions here on this line. And then when I went ahead and meshed that, I got this mesh, which is, okay, reasonable. Then I've applied a force on this surface here, and again that should be half the force that you expect to be applied in the actual problem. So now I'm still missing my symmetry. I haven't gone and done that, so let's just go same process as before. Click on model here, right click, and I go insert symmetry. And now we go into symmetry, and this time I have to put in two different symmetric planes. So I'm going to go insert symmetry region. and that's the first one. So it's looking for geometry selection. So let's select this one. So this is going to be the one that's at the X direction normal. So let's go OK to that. And again, like I said in the previous the truss example here, we're going to define the normal to this symmetry plane. So this symmetry plane is the YZ plane, and it's the X normal. What's the direction we want it reflected in? So in this case, that's already set to X. We don't have to do anything. So now we need to define another symmetry plane. So we're going to go Insert Symmetry Region again, and this time I'm going to pick the bottom face. I'm going to go Apply, and this time it's very, very important that we change this to be the Y. Okay, so it's the XZ plane, so the Y is its normal. So we must change that to Y. So now we've defined our symmetry. So now everything else is set up. So we have our two symmetry regions again. So we have this face and we have that face, and we've already got our load applied and our mesh done. So we should be able to go ahead and just solve that now. So it should be quite a quick solution. Okay, and then we can just look at our total deformation. So again, there's our deformed shape. Again, always useful to turn on the undeformed shape. So you can see that our plate has moved across in the horizontal direction, has gotten thinner in the vertical direction. And again, the hole is defined from being a perfect circle into more of an oval shape. And again, it's important to note this is exaggerated just for the purposes of display. Okay, so we just go back to our elements again. And again, we can get our stress. And again, the stress is, as we would expect in this problem, it's very high above the hull, so in this region here. Okay, so then as before, we can turn on those symmetry regions again. So we can just go back into symmetry here, click on this. So again, I'm going to follow the same methodologies that I did before. So I'm going to say I want, first of all, two versions of it. And I want half, and I want you to reflect across the x-axis, and so I'm going to use a very small number in there, 1e to the minus 6. So if we just take a look at our results now, let's take a look at normal stress. Okay, so you can see that we've reflected across the x-axis. Okay, we'll just zoom out a bit there. So now we've got, you know, half of the model, but we can continue going and getting the full model. So again, if you go back into symmetry, so if I move down to expansion number 2 now, and again do the same thing and say, well, I want 2, and I want you to use half the model again, and we're going to this time put it in the Y. Again, with the very small 1e to the minus 6 in the Y. So now I have two of these. I have graphical expansion 1 in the X, graphical expansion 2 in the Y. So if I go back to my results again, now you will see that I have the full model. So there's the full model plate with a whole model, and I've expanded the symmetry in both directions. So next we're going to move on to using symmetry in 3 dimensions, and in this case we just have a simple rectangular block with a hole in the middle. And if you look at this, and it's in tension both sides, equal tension. So if you look at this structure, you can obviously see we've symmetry through the hole this way, but we've symmetry again in the longitudinal direction here. But finally, we've got symmetry as well, just through the thickness. So there's actually 3 planes of symmetry we can use here, and we can end up modeling actually 1/8 of the structure. So again, just to make that clear, you can see here if I have the full structure, and I show the various symmetry planes I've used. So I have one plane here, I have one plane here, and then I have a final plane here. So I'm really left with just the top 1/4 over here. And again, just to show them what I'm left with, it's this bit here. Okay, so it's reflected across its bottom face. Okay, it's reflected across this face here, and it's also reflected across that face there. So just switching over to Workbench, I already have my model set up here. So again, just to show, I have a geometry. Okay, there's a geometry just shown on the previous slide. I've assigned a material model to it, just simple properties for steel. We've done a mesh. Again, you know, maybe not the best mesh in the world, but we just divided into equal elements and made them quite small. It'll do for the purposes of this video. And I've also applied a force on the end there. And I've already told it that I want to get things like total deformation and equivalent stress. So what I need to do to start off with is I need to, again, define my symmetry planes as before. So it's exactly the same as we did in 2D, and we're going to have 3 of them this time. So again, I right click on model, insert symmetry, and then when I click on symmetry, I'm going to go insert symmetry region. And it's asking me again for my geometry. I'll just this time make sure it's set to faces. Okay, so I'm going to start with this one, and that one is, its normal is in the X direction. So I'm going to go apply, and it's already set to X, so that's all good. Let's put another one in, insert symmetry region. This time let's pick this one here. and go apply, and this time its normal is in the Z direction. Okay, so we must change that to Z. And then finally we want to get to one on the bottom, so we're going to have to just rotate this around a bit so we can see that. So our final symmetry region, then we're going to insert again symmetry region, pick the bottom face here, go apply, and then just change that to the Y direction. And then I'll just, so that's in the Y, and I'll just move that around to the isometric view again. So now I have my three symmetry regions, X, Y, Z, and Y on the bottom face. Okay, so now I've already set everything up. I should just be able to do my solution, and I can get my deformation and equivalent stress, which are the two things that I've asked it for. So here's my deformation, here's my equivalent stress. Both of those kind of look more or less what I should be expecting. So now I'm going to do the symmetry expansion as before. So again, we go back into symmetry here. And on the first plane, we want 2. And again, we say that it's half. And this one, we're going to say the delta x is 1e to the minus 6. Okay, so again, if we go and look at our results now, I've expanded it in one direction. So let's go and do the other two directions as well. So again, second direction, again, change that to half. And again, this time it's going to be in the y, so 1e to the minus 6. And finally, in the third direction, again, I want 2 of them. I want to change that to half. And I want to change the delta z to 1e to the minus 6 as well. So now I should have my full model when I go back and click on deformation. So there you can see. Again, let's just zoom out to take a look at that. So there's my full model. Okay. And again, I can rotate that around and take a look at it, so you can see that the hole has gone into a more of an ellipse face, that like we expected. Again, we can turn on the undeformed wireframe to show us the original shape and see we've gotten a little bit of hollowing going on and a change in shape. And again, the same thing with stress. We can look at that as well. Okay, so that's planar symmetry in 3D. So the next type of symmetry that we're going to look at is axisymmetry. So again, if we take an example of this stepped shaft with a force on the end and it's held at the bottom face here, if we were to take a slice through that shaft and rotate that slice around 360 degrees, we would get the full geometry of the shaft. So again, this is the kind of slice we would take through. So this geometry, it's like take a slice and look at half that slice. And if we swept this around 360, we would get the entire structure there. So in our finite element analysis, then what we do is we must ensure that we build this on the y-axis. Okay, because it's automatically assumed that it rotates around the y-axis. And our finite element model would look something like this, and we get those kind of results. So we'll go into that in a bit more detail in Workbench, but just to point out something, just again, if we're trying to model, let's say, a hollow in cylinder, let's say it's a cylinder subjected to internal pressure, we would model the 2D slice that's rotated 360 degrees, and we'd put that a distance away from the y-axis. So that distance from the y-axis sets the internal radius, if you like, of the pressure vessel. Okay, so again, this other diagram down here shows if we have the same thing, so if we have a rectangle, so if we build the rectangle a distance or n away from the y-axis, we get a hollow cylinder, whereas if we use the exact same rectangle on the y-axis, we'll get a solid cylinder. So it's very important that you place your representative geometry in the correct place. So going over to Workbench then, you can see that I've already brought my geometry in and meshed it. But just to take a little step back, if we just go to the overview in Workbench, it's very important in this case that when you're using your geometry, so if you right click on geometry and bring up properties, and you just make sure that that's set to 2D. So by default that'll be set to 3D. You set it to 2D, it allows you to access the axisymmetric options. So once that's done, you can bring your geometry into Workbench. So again, here we have our geometry, and again, it's very important here that when you click on geometry, you come down here and you change this 2D behavior to axisymmetric. So again, by default, it will be probably plane stress or by body, but you must change it to axisymmetric for it to understand that it's axisymmetric. When we do that, then we don't actually need to define anything more in symmetry. So I've just inserted a symmetry here. So again, just by default, to just show you this is what it would look like, I would have to go and I can actually solve it without inserting the symmetry. Okay, so again, I'll just maybe show you that first. So I have my mesh done here, and again, this is already solved. I can just tell it to update just to be sure. So it's solved. I've got my total deformation and equivalent stress. The only reason I'd actually need to input the symmetry in this case is to actually get access to expanding the full model. So just to briefly go through here, what I've done is I have a force on the top surface here, I have a friction support there, I have no symmetry, I just ensured that it was built on the y-axis in Design Modeler, and I can go ahead and solve on it, which I've done already, and I've got the results. So now what I'm going to show you how to do is to expand that symmetry. So in order to do that, we need to go Insert, Symmetry again, and we don't need to do anything else here, we just need to go to the first thing here. So before we had Cartesian and we were expanding it in the Cartesian directions, this time you should see an option, because you're using axisymmetric, 2D axisymmetric should pop up, and by default it says I'm going to make 37 repetitions and there'll be 10 degrees between each of those. So that means it'll rotate the whole thing around 360 degrees. So if I look at my stress now, or deformation, and maybe go to an isometric view, you can see that I have the full model there. Okay, so it's rotated around 360 degrees. If I went back, if I didn't particularly want that, and let's say I instead of having 37 of them, I brought it down to let's say 18. We want about 180 degree rotation. Again, if I go down into my results now, you can see that it's only giving me 1/2 of the model. Okay, so again, that's how you do that in using axisymmetry. So again, very, very important that you if you're using axisymmetry, that you build your model on the y-axis, and that you ensure that when you bring your geometry in, that you change this to axisymmetric down here, and that it's changed to 2D in the main Workbench window. Okay, the final type of symmetry we're going to look at today is cyclic symmetry. And cyclic symmetry is, if you imagine, if we take a look at this structure here, it's easier to examine. If we just take a slice of a pie, so in other words, we're taking a small slice out of this, and we're noticing that that shaded region, it can be repeated several times around, will give the full structure. Okay, so it's possible to just model that slice, or basically a certain angle of the structure. Again, this is very useful here. Again, if we take things like turbine blades, propeller blades, fan blades, and so on. If you look at this fan blade and attach it to a hub here, if we just take the shaded portion of the hub and blade and repeat that around 4 more times, we'll get the full structure. So it's possible to make a cyclic symmetry model of this entire fan by just modeling one blade and applying the proper cyclic symmetry boundary conditions and using cyclic symmetry expansion. So what we're going to do today is we're going to take a look at this problem here, where we have some kind of like a wheel hub, and again there's the full structure there, and there's the full symmetry expansion. We're actually only going to model this portion of it here, so we're going to model 45 degrees, which is essentially 1/8 of the entire structure. So let's jump over to Workbench and see how we do that. Okay, so here we are in Workbench, and we've already modeled that structure. We've brought it into our analysis part of Workbench. We set up the materials. We have set up the mesh already, and now we have to go and set up the cyclic symmetry. So the first thing we're going to do is go into coordinate systems, and we're going to create a new coordinate system. So we're going to insert a new coordinate system. And let's just call this one, let's rename it the cylindrical coordinate system. So you can call that whatever you like. So again, we want to change that from Cartesian to cylindrical. And once we do that, then it's asking me for some geometry to define its origin with. Okay, so I'm just going to select this face here and then go Apply. So now I've set up my cylindrical coordinate system, and it's centered on, according to this face here, in the center of that circle. Okay, so now I can go, and again, maybe I'll just get rid of this. Maybe you wouldn't have symmetry set up already. So if you don't, you just, again, same old process, insert symmetry, and then when you click on symmetry, insert, this time cyclic symmetry. Okay, so the first thing it's saying is, what coordinate system do you want to use? Well, it's already identified that the cylindrical coordinate system, but if it hadn't, I'd change that. It's asking me for a low boundary and a high boundary. So basically that is the start and end angle through which the structure is defined. So the low boundary should be the one nearest to the x-axis, and the high boundary should be the one furthest from the x-axis. Remember, angle is measured from the positive x-axis. So I'm going to go in here and select this face as my low boundary, and just go apply. And then I'm going to go over here and select this face as my high boundary, and hit apply. So now you can see I have my cyclic high and cyclic low and cyclic high defined here. Okay, so now I'm all set up. So I've already meshed this, but it's going to remesh it because it needs to ensure that the mesh is aligned at the low and high boundary. In other words, we need to make sure we have the same mesh on this face and the far face. Okay, so again, it's just asking me to update my mesh. So I already have done that mesh. I know it's okay, but it's just going to fix it for me again. And then I have set up here, I have put a fixed support on the inside here, and I have put a tangential force on the outside there on that surface. Okay, so again, just a very, very simple analysis. So I'm going to go ahead and tell it to solve that. And I've asked it to work out total deformation and equivalent stress for me. So you can see there's my total deformation, there's my equivalent stress. But it's not expanded. It hasn't showed me the full model. So how do I fix that? So if I go back to, instead of this time you do not go into Symmetry to do that, you go into Solution here, and you'll notice that down here you have Cyclic Solution Display Number of Sectors. So I have done 45 degrees of my structure here. So again, I want to get the full 360 degrees. 45 into 360 is 8. So I need to have 8 repetitions to give me the full 360. Okay, so now you'll notice that it needs to reevaluate those results because I've done that. So again, I'll just say evaluate all results. And now if I click on total deformation, I've got the full model. Okay, so again, that's just a simple example for cyclic symmetry. And again, slightly different, but again, if you follow this process, you should find it reasonably simple. So that's the end of this Workbench tips video on using Symmetry in Ansys Workbench. So as always, if you want to find out any more information about anything I've discussed today, it's discussed in more detail in the book, Practical Stress Analysis with Finite Elements. So it's now its 3rd edition and available from Amazon and all good booksellers. Okay, so thanks, hope you found this video useful, and I'll see you in the next video.